So we know that V1 is equal to 2 minus V2. If you square that, you get V1 squared is equal to 4 minus 4V2 plus V2 squared. I'm also going to take this one, and everything will come out a lot nicer if I divide both sides by 0.05. Okay, so I'm going to do that just to simplify this. It's the same as multiplying by 20, so you get 4 is equal to V1 squared plus V2 squared. And now I'm going to substitute this one into this one. So you get 4 is equal to 4 minus 4V2 plus 2V2 squared. The 4's cancel, and you get 0 is equal to minus 4V2 plus 2V2 squared. Quadratic formula gives you V2 equal to 0 or 2 meters per second. Which one do we want of these two? We want 2. This was the velocity of the second mass before the collision, so we want this one. So after the collision, the ball that was initially at rest is now moving with the velocity that the other ball had before the collision. And now we can substitute this back into, so substitute V2 into 1b. So that says V1 is equal to 2 minus V2, which is 2 minus 2, which is 0. So the first ball stops dead. The second ball takes off with the speed it had. Not because of gravity, because of friction, though. Because of any kind of, energy losses and, friction. So yeah, there's air resistance. Probably the bigger losses of energy come from the fact that these aren't perfectly elastic. So it deforms, but it doesn't spring back fast enough to get all of that energy back. And so it loses energy in that returning to its shape. But it is pretty close, actually. I mean, it'll go for a long time, We have one in the lab. We have one of the executive models from back before all the budget cuts. We would only get the one ball system now. Any questions about that? Okay, that's it.